Welcome back, everyone. So next up, we have Adam Harper from the University of Warwick, and he's going to be talking to us about the distribution of short moving character sums. Enjoy, Adam.
Okay, so thank you very much, and thank you to the organisers for inviting me to speak here. So I have 13 slides, I think. So that will give me a bit of time to say something about Andrew at the start. So I was Andrew's postdoc here in Montreal for a year. And we have, I think, 3 joint papers together so far. And if you know anything about the kind of maths I do, it doesn't take much to see that it's very heavily influenced by the kind of things that Andrew does. And one of the interests that we share, I think, is character sums, about which there's already been a talk in this conference. And that's what I want to talk about today. So I hope you enjoy it, Andrew, and everybody else. And thank you very much, and happy birthday. So the plan for the talk is pretty conventional. So first, I want to describe the particular character sum problem I'm interested in. And I hope that even if you're not interested, not used to thinking about these things, this could be pretty easy to understand. And then I'll describe some previous work and some new work on this question, and say something about the proofs depending on how much time there is. And then I want to finish by talking about some open problems. And as you'll see, there's really a lot more that we don't know about this question than that we do know at the moment. Okay, so throughout the talk, R is going to be some large prime modulus, and chi is going to be a non-principal Dirichlet character to this modulus. And if you like, for a lot of what I'm going to say, you can just think of chi as being the Legendre symbol, except that the Legendre symbol, of course, is real valued, and most characters are not just real valued. So that will make a difference in some places. But if you prefer the Legendre symbol, just think of that a lot of the time. And this is the particular problem I want to consider. So I want to take a character chi and a length function h, so that will depend on R. I want to look at the sum of my Dirichlet character in the interval that starts x and is of length h. And so my notation here, s chi h of x, is supposed to reflect that. So for given R, chi is given, h is given, and x is the thing that's going to vary. So what we're going to do is look at the sum of our Dirichlet character as we slide the interval of summation around. And this will give a lot of different values, because as the start position of the sum moves, the sum will take different values. And I want to think about what's the distribution of these values for the different start positions of the sum. So since chi is periodic mod R, we can restrict to the case where we slide our start position between 1 and R. That's the interesting range. And equally, we can restrict to the case where length of the interval of summation, h, is between 1 and R. That's right. Okay, so that's the question. If I take my short interval, I sum the character over the interval, I move the interval around, what happens to the values? So if this isn't clear, nothing after this point will be clear. So please say now if this isn't obvious to you. Is this okay? Okay. And likewise throughout the talk, please interrupt if I'm going too fast, or if you're just interested in hearing more about something. Right. So this problem has been studied before. I think it was first studied by Davenport and Erd Hos in the 50s, in the particular case of the Legendre symbol. And so they showed that under some conditions on the length function h, which I'll come back to in a minute, if you take the character sum and you rescale it by the standard deviation, so square root of the length of summation, and you look at this where the start point of the sum is uniformly random over all the possible values, so uniformly random between 0 and r-1, this converges in distribution to a standard Gaussian, a normal one. And just to be absolutely explicit, convergence in distribution to a standard Gaussian means this. So if I look at the probability, the proportion of start points where this rescaled sum is at most z, this converges to the Gaussian CDF at z as r goes to infinity. Okay, and the important thing in this result is the conditions on h. So h has to go to infinity. That's very natural, because if I just have a bounded number of discrete things that I'm summing up, it's not reasonable to expect that to converge to a nice continuous limit like the Gaussian. But then there's also this condition that log h over log r goes to 0. So that's saying that h doesn't tend to infinity too fast, saying that h is at most r to the epsilon for any fixed epsilon. Okay, so we'll come back to that later. But under that condition, they get what I guess is the nicest possible behavior here, the Gaussian limit. So they did this for the Legendre symbol. I don't think there's any reason they couldn't have done it for more general characters. It's just maybe easier to state the result for the Legendre symbol. But it has more recently been done for more general characters. So Mack and Zaharescu did this looking at the real and imaginary parts of the sum separately, and some other things as well, and getting Gaussian limits for those. And then Yunus Lamzouri, who's here, did the full generalization of this. So he showed, so there's lots of uniformity here. So you can choose a non-real character model however you want, any non-real character. And under the same conditions on the function h as Davenport and Erd Hos, so it tends to infinity, but not too fast, you get convergence. And now, so if chi is a non-real character, this is a complex valued thing. Now, and so it converges to a standard complex Gaussian, the natural analog of the normal one. Where does this condition that log h over log r goes to 0, that h is at most r to the epsilon, come from? So that's because all of these proofs use the method of moments, which is something that's actually been mentioned already a few times in this conference, in Ken Omo's talk, and in Emmanuel Kowalski's talk as well. So to prove convergence to a nice distribution, to prove convergence to a nice distribution like the Gaussian, it's enough to compute all the power moments, so the average of the kth power of this quantity for all k, and show they converge to the corresponding ones for the target distribution. If you can do that and you get convergence, then you get convergence in distribution as well. But if you want to compute the average of the kth power of this for all k, so in this sum I have h terms. So if I have the kth power, I have h to the k terms. And in order for the method to work, you need that to be kind of small compared with r. So we need h to the k to be small compared with r for all fixed k. And that's exactly the condition here. Okay, so this comes up very naturally in the proof, but just because it comes up very naturally in the proof, no reason to think that that's the truth of the situation. And so in the same paper where he did the generalization to complex characters, Lamzouri made a conjecture about what should happen here. So I'm going to move over there so you don't always see my back on this side. So he conjectured that on a much bigger range of h, so h tends to infinity, but h is little o of r over log r. So not r to the little o1, not r to the epsilon, like in the proven results, but much bigger, much closer to r. You should still have convergence in distribution to the same limit, to the complex Gaussian limit. And I'm not going to say too much about where this comes from. You might hear a bit more about it in Sam's talk this afternoon, perhaps. But there's a fairly natural random model for Dirichlet characters, and a short interval problem being studied for that random model. And if you translate from the random model problem to the character setting, this range comes out naturally. So I should say that in the work of Chatterjee and Sand on the random model problem, they didn't show that x over log x would be the analog of r over log r here. So they didn't show that's the maximum range where you get convergence in the Gaussian, nor did Lamzouri conjecture that that was the maximum range. They just showed that you do get convergence in the Gaussian up to log of x over log x. And so he conjectured that you should get the same thing here up to log of r over log r. So are there questions about what I said up to here?
So beyond the range of r over log r, is there believed to be still Gaussian, or is it believed to have a different behavior?
Okay, I'll come back to that later. Other questions? Okay, so in previous iterations of his talk, I have stopped at this point and alarmed the audience by asking them to speculate whether they think the conjecture is true or not. So I'm not going to do that here, but since Andrew is right in front of me here, it seems too good an opportunity to resist. So Andrew, what do you think about the conjecture?
Please speak into the mic so we have it recorded.
I feel like I'm hiding for nothing here. I would guess it's true, but
okay. Because you think the random model is good, or for some other reason?
I would guess a bit like Yunus that the limit is the Chatterjee-Sand range.
Yeah. Okay. Okay. So let's discuss that a bit. So actually, I think this is a perfectly reasonable thing to say. So the random multiplicative model is a good one for lots of problems involving Dirichlet characters, actually, and the way it's being translated to this moving interval problem seems pretty natural. So I think it's a perfectly sensible conjecture to have made. If you just look at it, you might very well think it could be true. It could be, very well could be true, but there are some issues. So that's what I just want to point out. So Dirichlet characters have two properties, right? They have multiplicativity. That's very well captured by the random multiplicative model, but they also have periodicity mod R, which isn't captured at all by the random model. So for some questions, especially questions that only involve the character on quite small numbers, so where you don't really get close to the period, the periodicity maybe doesn't matter. So the random multiplicative model just translates over very directly. And if people know a bit more about this, the range where you expect to start having problems is maybe about square root R. This is the point where you see the Fourier flip, for people who know about that, or where you have the reflection in the approximate function equation. But the problem I'm discussing here is a problem largely about large values of n. So as I move my interval round, most of the start points of the interval are going to be pretty big. So most of the n values at which I'm looking at chi are going to be pretty big. So this is a problem where potentially the periodicity could intervene. Now, the other thing is that what's a random multiplicative function? So it's a randomly chosen function with multiplicative properties. So if that models characters, what it would seem to model is a randomly chosen Dirichlet character. So a fixed short interval and then a random character on that interval. And that's not exactly the situation here. So here we have a fixed Dirichlet character at an interval that's randomly moving around. And it's not so clear that you should have necessarily the same answer. Now, it turns out that indeed the conjecture is not quite right. It's a bit too strong. So here's a theorem. So if I take my length function h to be r divided by any fixed pair of log, so log r to the power of a, then I can find some bad characters so that when I look at my rescaled short interval sum with the random start point, this doesn't converge in distribution to the expected complex Gaussian limit. So for intervals of this length, there are bad characters where things go wrong. And in particular, if I take a is 2 here, for example, so this is r over log squared. This is little o of r over log r. So Lamzouri's conjecture would be predicting that you should have convergence on this range, and you don't necessarily. So as r varies. So as r goes to infinity, I can find a bad character mod r. So when I go along this sequence, actually lots of characters, but yes, okay. And I stated this in the complex case, you can do the same thing for real characters. So for real characters, there's only one Legendre symbol, mod each r, each prime r, but there's a bad subsequence of primes r, so that when you go to infinity along this bad subsequence, you don't get convergence to the Gaussian. Okay, so let me talk about the proof of this theorem a little bit. So since characters are periodic mod r, these short interval sums, they're also periodic mod r in the x variable. So they have a nice Fourier expansion, which it turns out looks like this. So if I take my sum and I rescale it by square root the length of the interval by the standard deviation, I get some prefactors. Don't need to know what they are. This is the Gauss sum. It has size square root r. You probably don't even need to know that for what I'm going to say. And then here is the Fourier expansion. So we have a sum of some complex exponentials. The kind of amazing thing about Dirichlet characters is that they're their own Fourier transform, basically. So on the physical space side here, I have Dirichlet characters. The Fourier coefficient is also a Dirichlet character, up to a conjugate and a minus sign. So that's a kind of amazing thing. And on the physical space side, my original interval has length h. And the conductor, the kind of complexity in this problem is r. So on the Fourier side, I get a sum of length r over h. Okay, that's what you'd expect. And if h is this, and I plug that in here, I get a sum here of length, some big pair of log r to the power a. So pretty short, that's the main point. So long intervals here translate to short sums on the Fourier side. Okay, so now, so Andrew, we're going to use some of your work. So, so on intervals of this length, there exist characters which, I've written very vaguely here, look sort of like 1. So this is a result of Granville and Sand from about 20 years ago. So sort of like 1 means that when you take the sum on this interval, you don't get too much cancellation. So the sum is at least some constant depending on a times the full length of the range of summation. Okay, why does that help? Well, let's just pretend for a moment that they didn't look sort of like 1, they're actually just 1. So if we had a character that was just 1, then this thing would be some prefactors, some scaling, and then just a sum of 1 times this complex exponential. So that's a Dirichlet kernel, or a geometric progression, which you could just explicitly compute. And the way that Dirichlet kernels work is when x over r is small mod 1, when x is small mod r, they take very large values. But when x over r is not small mod 1, they take pretty small values. So they certainly don't have a Gaussian looking distribution as x varies. Okay, so if you could just replace chi here by 1, you'd be done at this point. This definitely isn't Gaussian. Now, let me just say a word about how you actually do this proof, because I think it's worth thinking about how you would prove something doesn't converge in distribution.
So to be a little bit more specific, when you're saying when the length is very short and these sums get large, but what is this more precise threshold where these sums become small?
So for any fixed power of log, there's some constant that depends on A. You can find characters where the sum is at least this small constant depending on A times the full length. Once the length of the interval is bigger than any fixed power of log, then you start to have, assuming GRH, you start to have cancellation. Okay, so we know that you can prove convergence to a nice limit like the Gaussian limit by computing moments and showing they all converge. So you might think showing we don't have convergence, that should be even easier. You just start computing moments, you show they don't converge, and then you're done. But that's a big mistake. So it's perfectly possible to have convergence in distribution to a very nice limit like the Gaussian with lots of moments blowing up. So you need to do something a bit smarter than that. So what you actually do is you say, I'm going to take my sum here, I'm going to subtract from it a suitable multiple of this Dirichlet kernel. So this Dirichlet kernel, I said it doesn't converge in distribution to Gaussian. Actually, it converges in probability to 0 when the x is uniformly random. So subtracting that won't make any difference to the supposed convergence in distribution of this sum. But what it will do if you choose your multiple correctly, depending on the amount of cancellation you have here, is it will reduce the variance of the sum because there'll be a non-trivial mean value of these chi's, which are then removed. So now, if this was supposedly converging in distribution to the complex Gaussian limit, you'd have something with variance strictly less than 1, uniformly bounded less than 1, after I've subtracted this piece, converging to something which has variance exactly 1. So that's how the proof actually goes. So maybe are there any questions about that?
This seems to rule out convergence to the standard Gaussian.
Yes.
But it does not rule out that you get a Gaussian with smaller variance.
That's an excellent question. Yes, it does not rule that out. I agree.
Break the correlation between the characters in the multiplicative additive.
So you don't need to do anything really. So what I'm saying is I'm going to subtract a piece here, which reflects the mean value of these chi's. Then when I compute the variance, so I compute the variance on two sides, right? I can do it the way that you kind of most naturally do it on the physical space side, or I can do it on the Fourier side as well. And on the Fourier side, when you compute the variance, you get pieces corresponding to the different Fourier modes. This is just Parseval. If I subtract a piece that corresponds to the mean values of the chi's, I'm getting rid of the 0 Fourier mode. So I'm taking away a piece of the variance. If this were a typical character where you didn't have, where you have lots of cancellation, the piece I'd be subtracting would be negligible in size. But for these special characters where you don't have much cancellation, this is an actual piece that's being removed. Right. So this is all a bit negative, maybe. So let me state a positive result as well. So Lamzouri's conjecture is not quite right, but actually it's almost right in some sense. So these characters that Granville September produced, there are actually quite a few of them for each R, but most characters don't look like that. For most characters, if you sum over this range, you will have cancellation. And so you might expect that at least for most characters, the conjecture could be right. And here's a theorem which says something like that. So under some conditions on H, which I'll again come back to in a second, there's a good set of characters, mod R. There are a lot of characters in the good set. So most characters belong to the good set when R becomes large. And if you restrict yourself to characters from the good set, you do get convergence in distribution to the expected Gaussian. Okay, so what are the conditions on H? So one is that H is little O of R. So this is actually even wider range than Lamzouri conjectured. And it's very natural to expect that you can't have H of the order of R for similar reasons I discussed before, because if H is of the order of R, you just have a bounded number of terms in the sum here. And again, something which is a bounded number of sort of structured pieces has no right to be converging to a nice Gaussian limit. Then there's this unfortunate other condition here. So this is saying that H is kind of close to R. So H is bigger than R to the 1 minus epsilon for any fixed epsilon. And this again arises because there's a use of the method moments in the proof of this. So this probably shouldn't need to be here, but this is an actual condition. Okay, so for reasons of time, I won't discuss the proof of that now, but if people are interested, they can certainly ask. So I want to finish by kind of speculating what might be true in this question. So this is getting back to what was asked earlier, and stating some open questions and also a health warning for one of these open questions. So here's a kind of tentative replacement for Lamzouri's conjecture. So maybe if H tends to infinity, but under this condition on H, so this is saying that H is smaller than R divided by any power of log. Okay, so this is saying that r divided by h is bigger than any fixed power of log, so h is smaller than r divided by any fixed power of log. Maybe under this condition, you do have convergence and distribution to the obvious Gaussian limit. And I would conjecture the same thing for the Legendre symbol as well. So this is the most that could be true. Okay, so the negative result theorem, whatever it was, theorem 2, I think, said that if you don't have this condition, there are bad characters where you don't have this convergence. So this is the strongest thing that could be true for all characters, and I conjecture that this might be true. So, okay, here's an open question, prove this. But before you get started on that, I'll give you a little warning. So to do that, you're going to need to know that the construction used in theorem 2, the negative result, couldn't be extended to a bigger range. Because if it could, you could just transfer the proof directly over. So all that was required was that we had these characters that didn't have much cancellation on these intervals of length, some big power of log r. And unfortunately, our knowledge of these questions is somewhat limited. So you need to know that the character sum up to r over h has cancellation on this range. We only know this when the length of the sum is like r to the 1/4 or more. That's the Burgess band. So if you're going to attack this, you probably want to assume something like GRH, under which we do know this, or at least that you have cancellation in this sum. Okay, or if you don't assume these things and you go ahead and prove the conjecture anyway, well, great, but you probably then don't want to be selling it as a proof of the conjecture, but as a proof of the generalized Riemann hypothesis or something like that. I should say, though, that even if you do assume GRH or this kind of statement, it's not clear how to go on to do anything more. So it's not that GRH is going to do all the work here. You're probably going to need to assume some arithmetic content like this, but even if you assume that, what you're going to go and do then, it's not so obvious. So even doing something in the almost all case, it's not clear what to do. So the old results of Davenport and Erd Hos and the complex version of this by Lamzouri, they work when h is pretty small. It's smaller than r to the power epsilon. And the new results that I was describing work when h is kind of close to r. So these are the cases where you can compute the moments either on the physical side or the Fourier side. If h is kind of in the middle, then we seem to be completely stuck. So for example, when h is square root r, it's very unclear how to proceed. Even doing something for almost all characters on this range, it's not clear what to do. It's actually a manifestation, quite a general problem that comes up a lot in number theory. So there are lots of settings where you'd like to prove convergence to some nice limit, some Gaussian limit. You expect it to be true on a very wide range of the parameters, but the only thing we know how to do is to compute moments, and that greatly restricts the range on which you can do anything. Yeah, so that would be the ideal here, to come up with some kind of more general method that can replace the method of moments in lots of these questions. But this is a particular thing that I'd be very happy if somebody could attack. I don't see how to do it. Right, and that's it. I think that's all I want to say. So thank you very much for your attention, and happy birthday again.
Thanks a lot. Any questions for Adam?
Just, your normalizations, you're looking at square root h size.
Mm-hmm.
So why can't you do this more uniformly? Go beyond just the power of log?
Power of log where?
The construction, right, is h over power of log,
Yes.
h to the a.
Yes.
But that's just a constant in the mean value. There's a constant, but you can get the mean value bigger than square root h in a much larger range.
Right, but
So I'm confused.
okay, let me see if I can go back. So I need really no cancellation at all. So I need the sum of chi over this interval to be within a constant factor of the total length. The contribution from the Dirichlet character on this, when summed up over this interval, this is what's going to be subtracted from the variance in this argument to show that you don't get convergence. So this needs to be a kind of order 1 piece. So the rescaling by square root h is the natural rescaling. Everything now is on the order 1 scale, typically. So I need the thing I removed to also be on the order 1 scale. Yeah. So if you work out the size of all these things, this should have size like order 1 if you have roughly square root cancellation in the sum on the top. Equally, this should have size order 1 if you have roughly square root cancellation.
If for your conjecture you don't seek the full Gaussian claim, but just to get the expected variance is what you expect. Is that correspond to just some weird character, some estimate or something? Is there something explicit?
Yeah. So on the range where h is small, the way that you actually do these computations is you end up using the Weiband for character sums.
Right.
So yeah, when you expand everything out, this is going to be some big character sum you need to compute. To actually do the computation, the only way we seem to know how to do it is if the number of kind of off-diagonal terms is pretty small and you apply the Weiband for all those and you have a small number of terms.
Right.
There could conceivably be much more cancellation between these sums,
Right.
but we don't know how to extract
But
it.
in this kind of regime where h is very close to r, you use the Fourier
Yes.
expansion, and then you compute this. You could compute the variance on the Fourier side.
Yes,
And so that should give you some sort of double character sum or something.
yes, that's right.
So I mean, there's some explicit character sum claim that would be like a special case,
Yes.
morally at least,
Yes.
of your conjecture.
Yeah, so I mean, in a way, that's how the proof is working, right? So you're showing for these characters the variance is the wrong thing to be the standard Gaussian variance. Yeah, that's right. So any particular moment would translate to some potentially complicated looking character sum on the Fourier side or the physical side. The number of moments that you could compute gets smaller as the length of the sum either on this side or on this side gets.
Can anything be said about the same problem where chi is multiplied by Mobius function?
I don't see how, because, well, let's see. So on the physical side, you then end up with sums of characters with lots of shifts twisted by Mobius. So you don't have the Weiband, so it's not clear what to do. On the Fourier side, you don't have the nice Fourier expansion where you just get the Dirichlet character here again. So I think the answer is no. At least I don't see how to do it by any kind of natural variant of these methods.
But you still think it will be Gaussian?
So I mean, it's conceivable that when you have the Mobius twist, you should get Gaussian even a wider range than for characters, right? Certainly true that in other character sum problems, there are kind of characters that behave weirdly. And when you twist by Mobius, you get rid of these topologies. So you might even have nicer behavior twisted by Mobius, but it's very unclear how to prove it.
So what about for random multiplicative functions? What do you do?
Okay, so I will defer some of that maybe to Sam's talk this afternoon when he might say something about it. So I could maybe say, right, so on this third point here, I said that it's not clear that the fixed short interval on the random multiplicative function is a good model for this particular question. Now, recently there's been some nice work, including by people here in the audience, I think, on actually looking at maybe the more natural random multiplicative analog of this problem. So that's where you move the interval round in some kind of a long ambient interval, and you ask what happens for almost all realizations of the random multiplicative function. And what they know how to do is that if the length of the interval is up to x divided by some big power of log, actually some power of log that goes to infinity if you want the full Gaussian limit, then for almost all realizations of the random multiplicative function, you get convergence to the Gaussian. So that's what's known on the random multiplicative side. It's clear that, so the periodicity is really doing something here. So on the random multiplicative side, once the intervals get close to r in length, if r is the kind of start point, then even for most realizations of the random multiplicative function, you won't have convergence. The Gaussian, you have too much cancellation, you have this more than square root cancellation phenomenon. Whereas, as I showed you in the positive theorem for Dirichlet characters, you do have convergence to the Gaussian, even for intervals of length little o of r for most characters. So there's definitely a difference between the settings for very long intervals. Where this difference starts to rise is what's obvious.
But can you just take the Fourier flip and then look at the random model on that side?
Right, that's a good question. So the answer is no, because this step here uses the fact that you're working with Dirichlet characters. So a random multiplicative function is not its own Fourier transform. What you could do, it's an interesting question in its own right, is just to study this with the random multiplicative function there. Okay, and that's actually how the proof of the positive result, the almost all result works. Yeah, so that's an interesting question. The question where you move the interval round for the random multiplicative function is another interesting question. These are not the same question. Right. So I think that's a good general philosophy. So if you're working with chi on values up to root r, which is where the Fourier flip happens, just use the random multiplicative function. If you're working past that range, you need to do something else to encourage the periodicity.
I want to renew the question from earlier, I guess. Did you compute something
I mean, you showed that the variance is less than 1.
Yes.
But did you compute, let's say, the fourth moment and show that it's incompatible with the variance as far as a Gaussian would be concerned?
I didn't do that. So what I would expect should happen here is, okay, so if A is less than 1, then we can find characters which don't just have not much cancellation on this interval. We can find characters that actually have essentially no cancellation on this interval. So then you have something which is converging probability to 0 with any natural rescaling. Once A gets bigger, then who knows quite what's going on here. I guess I find it hard to believe that you could have convergence to a Gaussian with not the natural variance. It does happen in some problems. I don't see why it would happen here, but I don't know. So this is a very kind of limited amount of information that we have. We just know that you don't have convergence to the Gaussian with the obvious variance. We don't know if you have convergence to any limit distribution. If it's a Gaussian, anything else about it. So there are lots of questions here.
Any final questions for Adam?
It's not relevant here. It's not relevant here. Okay, in the proof of this, there's well, something vaguely like pretentiousness. I should have said so for smooth friable numbers people. This is a friable numbers argument.
On that note, let's have a break. But first, let's thank Adam, and then we'll thank all the speakers in this morning's session. Oh no, there's one more talk. So after Vivian's talk, we'll thank all the